Take 5 numbers, 0, 1, pi. The number e and I, the square root of -1. These 5 numbers come from completely different branches of mathematics. They have nothing in common, they shouldn't be connected, but in 1748, a Swiss mathematician named Leonhard Euler proved they are. He wrote down one equation and it connected all of them. E to the power of I times pi plus 1 equals 0. Richard Feynman called it the most remarkable formula in mathematics. This is the story of why it's true. Before we can understand why this equation works, you need to meet the 5 numbers in it, because each one was discovered independently, in different centuries, for different reasons. 0, invented in India around the 5th century, a placeholder that became a number, the concept of nothing given a symbol. 1, the unit, the foundation of counting. Every number is built from ones. Pi, the ratio of a circle's circumference to its diameter, known to the Babylonians around 1900 BC. Irrational. Its digits never end, never repeat. 3.14159. E, discovered by Jacob Bernoulli in 1683 while studying compound interest. It's the base of natural growth, 2.71828. Also irrational, also never-ending. And I, the square root of -1. For centuries, mathematicians called it impossible. Raphael Bombelli first used it seriously in 1572. It doesn't exist on the number line, it lives somewhere else. 5 numbers, 5 different origins, 5 different purposes, and somehow Euler found the thread that connects them all. Here's the problem. What does it mean to raise a number to an imaginary power? You know what a squared means, e times e. You know what a cubed means, e times e times e. But e to the power of I, that doesn't make sense in the usual way. You can't multiply e by itself, I times. So we need a different definition of exponentiation. And that's where Taylor series come in. In the 1700s, mathematicians discovered that you can write any smooth function as an infinite sum of terms. For e to the x, that sum is e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, forever. This works for any x, any real number, but here's Euler's insight. What if x isn't real? What if x equals I times theta? Let's substitute. Replace x with I theta. The first term is 1, the second is I theta. The third is I theta squared over 2 factorial. But I squared is -1, so that term becomes negative theta squared over 2. Keep going. The pattern splits into 2 groups, the real parts and the imaginary parts. The real parts are 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. That's the Taylor series for cosine. The imaginary parts are theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. That's the Taylor series for sine. So e to the I theta equals cosine theta plus I times sine theta. That's Euler's formula, published in his 1748 book, Introductio in Analysin Infinitorum. But what does this formula actually look like? Let's draw it. Imagine a flat plane. The horizontal axis is real numbers. The vertical axis is imaginary numbers. This is the complex plane. Now, e to the I theta is a point on this plane. Its real part is cosine theta. Its imaginary part is sine theta. If you remember trigonometry, cosine and sine are the x and y coordinates of a point on the unit circle. So e to the I theta traces out a circle. As theta goes from 0 to 2 pi, the point walks around the unit circle. At theta equals 0, you're at the point 1. At theta equals pi over 2, you're at I. At theta equals pi, you're at -1. Let me say that again. When theta equals pi, e to the I, pi, equals cosine pi, plus I sin pi. Cosine of pi is -1. Sine of pi is 0. So e to the I, pi, equals -1. Add 1 to both sides. E to the I, pi, plus 1 equals 0. That's it. That's Euler's identity. It's not a trick. It's not a coincidence. It's what happens when exponential growth meets rotation in the complex plane. Mathematicians don't just call this equation correct. They call it beautiful. Why? First argument, economy. 5 fundamental constants. 3 basic operations. Addition, multiplication, exponentiation. 1 equation. Nothing is wasted. Nothing is extra. It's the mathematical equivalent of a haiku. The physicist Benjamin Peirce, after proving the identity in a lecture at Harvard in 1866, reportedly said, "It is absolutely paradoxical. We cannot understand it, and we don't know what it means, but we have proved it, and therefore we know it must be the truth." Second argument, unexpected connection. Pi comes from geometry, circles. E comes from calculus, growth and change. I comes from algebra, solving equations that have no real solutions. These 3 worlds had no reason to be connected, but they are. Euler's identity is the proof. Third argument, depth. This isn't just a pretty formula, it's the foundation of signal processing, quantum mechanics, electrical engineering, and fluid dynamics. Every time you use a Fourier transform, you're using Euler's formula. Every time a physicist writes a wave function, e to the I theta is there. The equation that connects 5 constants also connects 5 branches of science. But here's something most people don't know. Euler wasn't the first to see this connection. In 1714, 34 years before Euler published his formula, an English mathematician named Roger Cotes wrote down a closely related result. In his paper, Logometria, published in the Philosophical Transactions of the Royal Society, Cotes showed that II times x equals the natural logarithm of cosine x plus I sine x. That's Euler's formula in logarithmic form. Flip it around and you get d to the ax equals cosine x plus I sine x. But Cotes died in 1716. At age 33, Newton himself said of Cotes, "If he had lived, we might have known something." Euler, working independently 30 years later, derived the same result using a completely different method through infinite series rather than geometry. And it was Euler who recognized the full power of the formula, who connected it to the 5 constants, and who published it in a form the world could use. The formula bears Euler's name, but the ghost of Roger Cotes deserves a mention. 5 numbers from 5 different worlds, 1 equation that ties them together. E to the I pi plus 1 equals 0. It tells you that growth and rotation are the same thing, that circles and exponentials speak the same language, that the imaginary is as real as the real. Next time you see this equation on a t-shirt or a coffee mug, remember, it's not decoration, it's a window into the deepest structure of mathematics. And it took a one-eyed Swiss genius to open it.